Today we're gonna learn integrating rational functions of sine and cosine using the z-substitution. But before going further, we have to discuss some things or recall some things which you probably have discussed in class. You recall um, that in z-substitution, we're going to let z to be equal to the tan of x over 2, and that implies that dx will simply be 2dz over 1 plus z squared. And also, I'm not going to prove this one because this is already discussed in class. The sine of x can be represented in terms of z as 2z over 1 plus z squared, and the cosine of x will simply be 1 minus z squared all over 1 plus z squared. Now, if you notice about this one, most of the, or at least all except z, has the term 1 plus z squared in the denominator. So maybe that's something that will help you recall the z substitution. Now, when is z substitution used? Z substitution is used for rational functions of sine and cosine. It means if you have some integral containing, say, a plus b, where a plus b is a function of sine and cosine. Now, in this specific example, we have to integrate the integral of dx all over 5 plus 4 cosine of x. Now, to do this, we are going to use the z substitution. Now, this integral can be rewritten as dx is simply 2 dz all over 1 plus z squared plus c squared. And everything is divided by, since that's just the dx part, everything is divided by 5 plus 4. Now, cosine of x, if you notice here, is simply 1 minus z squared. So we got 1 minus z squared all over 1 plus z squared. Now we have converted everything in terms of x. If you notice, originally we are dealing with terms of x. Now our integral becomes expressed or is expressed in terms of z now. So that's basically the gist of z substitution. All right, so we're now simplifying the integral. So I'm just going to copy the numerator. It's 2dz all over 1 plus z squared. And the denominator is, I'm going to take out the LCD of this one, which is 1 plus z squared. So if I have 1 plus z squared there, and this one will simply become 5, should be 5 times 1 plus z squared. And the next term is plus, I'm going to extend this one. This will just be 4 times 1 minus z squared. I'm going to extend this one just to distinguish that this is the larger over, if you if you understand what I mean. Now simply going to simplify this further. This will become 2dz. Actually, the messy part is the simplification part, plus z squared. And if you remember, just have you to recall this one. If you have a over b, which is just this part here, and if you divide that by some fraction c over d, I think you can still recall that that will just be equal to a over b multiplied by the reciprocal of the denominator, or d over c. So that's exactly the same algebra that we're going to perform here. This is telling me that I will have 1 plus z squared, or the denominator of the denominator. So 1 plus z squared, and I have 5 times 1 plus z squared, or simply the numerator part of the denominator. I'm hoping that is not confusing for you. 1 minus c squared. And that. Now, upon doing that, it's very clear that the 1 plus z squared part will cancel out. And that's a good thing because we want to simplify our integral. So we now have the simplified version to be 2dz divided by 5 times, I have to move this over, 5 times 1 plus z squared, and then we have plus 4 1 minus z squared. So I think you can still guess. We can further simplify this one. We have 2dz and then distribute 5 on the first term. So we have 5 plus 5z squared and then distribute the 4. So have 4 minus 4z squared. Now I can further simplify this one. By the way, I'm just going to take out the constant 2 out of the integral and I will just have dz all over. So notice that you have, let's deal first with the numbers. We have 5 and 4. So 5 plus 4 is simply 9 plus the variables, the terms containing variables. We have 5z squared minus 4z squared. So we simply get z squared. Now I'm going to rewrite this one into a very specific form because that will help us solve this one. So this will just be dz all over 3 squared plus z squared. Now why I did this, because I want you to recall this one. Although I can actually perform another technique on this one, but since we're using z-substitution, I'm not going to do that. I'm referring to rational functions, but you have to recall this one from your table of integrals, that whenever you have this very specific form of the integral of du all over a squared plus u squared, you have the result that is just 1 over a, just going to write 1 over a tangent inverse of u over a plus c. Now this is a result from your table of integral. But then again, probably in your class, once I'm going to create a video about partial fractions, and you might have to perform the integration of this using partial fraction. But for now, since our focus is z-substitution, I'm going to use this result from your table of integrals. Now, what this is telling you is that your dz in this case is simply equivalent to the du part here. It's just a du part here, and your 3 squared. This is telling you that a is 3 and your u here is the z part there. So that means to say that I can rewrite this, or this integral is simply equal to 2 multiplied by 1 over a. According to this form, it's 1 over a, but as I've said, a is 3, so I get 1 over 3. And then we have the tangent inverse of u. Now our u in this case is z, so that's gonna be z all over a. So it's a. Our a is 3, so that's z over 3. And then you you add the integration constant c, since we are dealing with an indefinite integral. Now I'm going to simplify this one. This will become 2/3 tangent inverse of z all over 3 plus c. Now, if you're going to encircle this one or box this one as your final answer, then that's not really a good idea, because if you notice that we haven't returned, if you go back to your integral, it's actually a function, or is a variable of x. X, if you notice. And our answer here is in terms of z. So that doesn't make sense. So this is telling us that although this is the answer in terms of z, we're going to return the variable to its original variable, which is in x. So you simply substitute the value of z in terms of x. Now recall that we actually let initially our z, this is the standard thing to do in z-substitution, we let our z to be equal to the tangent of x over 2. So we're going to do that same thing over here. So this will now become the tangent inverse of z is just tan of x over 2 divided by 3. So maybe I should put, or just to be safe, tangent inverse of that one and tangent inverse of that one plus c, the integration constant. Now, if you want to simplify this further, you should get this one. This will become, no, no, yeah, this one. You cannot simplify this further. It's 2/3 tangent inverse of, say, 1/3 of tangent x over 2 plus c. All right, so this is how you do your integration using the z-substitution. The salient thing that you should remember is the following substitution. You let z be equal to the tangent of x over 2, and that implies that your dx is just 2dz over 1 plus z squared. Everything, or your sine of x, will be expressed as 2z over 1 plus z squared. Your cosine of x will be 1 minus z squared all over 1 plus z squared. And in order for you to recall this easily, most of the terms are actually expressed in terms of z as 1 plus z squared, 1 plus z squared, and 1 plus z squared.